When does the universe end is a question that often feels simpler than it really is. Many people imagine the universe moving toward a final moment, a last event when everything either collapses inward or fades away completely. In everyday explanations, this ending is sometimes described as a single point in the future, a time when the universe stops existing in a clear and decisive way. That picture is familiar, intuitive, and easy to hold on to. Yet when scientists study the universe carefully, they find that this idea of a clean ending does not fully match how physical systems behave over time. In scientific discussions, the end of the universe is not usually framed as a sudden disappearance. Instead, it is described through gradual changes in temperature, structure, and energy. Observations show that the universe evolves slowly, through processes that unfold over immense spans of time. Even when there is disagreement among scientists, that disagreement is rarely about whether the universe will suddenly stop. It is more often about how conditions will continue to change and which trends will dominate far into the future. This video approaches the question calmly, without urgency. The science surrounding the universe's future is layered and subtle, and it does not resolve into a single dramatic conclusion. We will explore it step by step, staying close to what can be measured and inferred, and allowing each idea to settle before moving on. Welcome to AstraFlow. Here, science drifts quietly, and understanding comes without effort. If you'd like, you can share your thoughts below, or subscribe for more quiet explorations. Now, let's begin. To talk about when the universe might end, it helps first to consider what scientists mean by an ending at all. In everyday life, endings are often marked by events. A light turns off, a sound stops, a process reaches completion. These endings are usually clear because they happen on timescales that are short compared to human experience. The universe, however, operates on scales of time and space that are far larger than anything we encounter directly. Because of that, its changes do not announce themselves with sharp boundaries. In cosmology, the universe is treated as a physical system. It contains matter, energy, radiation, and space itself, all interacting according to well-tested laws. When scientists ask about its future, they are not looking for a final moment in a dramatic sense. They are examining trends. They ask whether temperatures increase or decrease, whether structures grow or dissolve, and whether energy remains available to drive change. One of the most important observations shaping these questions is that the universe is expanding. Distant galaxies are moving away from each other, not because they are flying through space in a conventional sense, but because the space between them is stretching. This expansion has been measured carefully through multiple independent methods, and it provides a baseline for nearly all modern predictions about the universe's future. Expansion suggests that, over time, matter becomes more spread out. As space grows larger, the average density of matter decreases. This has consequences that are slow but persistent. Stars form from dense clouds of gas, but as material becomes more diffuse, the conditions needed for new stars become harder to achieve. Heat spreads out, energy gradients flatten. None of this requires a final event. It happens continuously. Another key idea in these discussions is energy. The universe contains a fixed total amount of energy, but not all energy is equally useful. Over time, energy tends to move from concentrated forms to more evenly distributed ones. This principle is captured in the concept of entropy, which describes how systems evolve towards states that are harder to change. High entropy does not mean destruction. It means uniformity. It means fewer differences that can drive new processes. When scientists speak about an eventual end, they're often referring to a state in which the universe reaches a kind of balance. Temperatures approach the same value everywhere. Large-scale motion slows. Structures that once stood out begin to fade into the background. This state does not arrive suddenly. it is approached gradually, over spans of time so long that ordinary units like years become almost meaningless. Importantly, none of this implies that the universe vanishes. Space continues to exist. Particles continue to exist. What changes is the activity level. The universe becomes quieter, not because something stops it, but because the conditions for change slowly disappear. There are other ideas as well, and later in this exploration we will touch on them carefully. Some models imagine a future collapse where expansion reverses. Others consider more exotic possibilities tied to the behaviour of space itself. But even these models describe long, drawn-out processes rather than sudden endings. They depend on measurements that are still being refined, and they remain conditional rather than certain. For now, it is enough to notice that the common image of the universe ending in a single moment does not reflect how cosmology usually works. The universe does not behave like a machine with an on-off switch. It behaves more like a system that slowly changes its state, guided by simple rules applied over extraordinary durations. As we continue, we will stay grounded in what observations show and how scientists interpret them. We will move from familiar ideas toward more abstract ones, always at a steady pace. Each step will build on the last without rushing toward conclusions. When scientists talk about the end of the universe, one of the first things they clarify is what the word end actually means in a physical sense. Outside of science, an ending usually implies disappearance or failure, something that stops functioning altogether. In cosmology, the word is used much more carefully. It refers not to a moment when the universe is gone, but to a point at which its large-scale behaviour no longer changes in meaningful ways. In this context, an ending is defined by conditions rather than events. Scientists look at temperature, energy flow, structure, and motion. They ask whether stars can still form, whether matter can still clump together, and whether energy differences remain that allow anything new to happen. If those processes gradually slow and eventually cease, the universe is said to have reached its end state, even though it continues to exist. This way of thinking can feel unfamiliar because it removes drama from the question. There is no final explosion, no universal shutdown. Instead, there is a slow approach toward equilibrium. In physics, equilibrium describes a situation where opposing processes balance out, leaving no strong direction for further change. A cup of hot water cooling in a room is a simple example. It does not end abruptly. It gradually reaches the same temperature as its surroundings, and then it simply remains there. On a cosmic scale, the same principle applies, but over incomprehensibly long periods of time. The universe began in a hot, dense state, with enormous differences in temperature and energy from one region to another. Those differences drove rapid change. As time passes, expansion and interaction smooth those differences out. The universe becomes more uniform, not because something forces it to stop, but because there is less contrast left to drive motion. This is why cosmologists often avoid asking when the universe ends in terms of a date. Instead, they ask what the universe tends toward. They study whether temperatures continue to drop, whether structures become more isolated, and whether usable energy becomes scarcer. These trends matter more than any hypothetical final moment. One important detail is that none of this requires every process to stop at once. Different regions and systems evolve at different rates. Stars can continue to shine long after galaxies stop forming. Compact remnants can persist long after stars themselves fade. The end is therefore not synchronized. It is spread out across time, uneven and gradual. By framing the question this way, cosmology remains closely tied to observation. Scientists measure what exists now and model how those measurements change when extended forward. The universe's future is treated as a continuation of its present behaviour, not as a separate chapter governed by different rules. As this idea settles, it becomes easier to see why the universe's ending is often described as quiet rather than dramatic. It is defined by diminishing change, not by destruction. With that understanding in place, we can begin to look more closely at the universe itself as a system, and how its basic components shape everything that comes after. To understand how the universe might reach an end state, scientists first describe it as a system. In physics, a system is a collection of components that interact according to consistent rules. The universe, taken as a whole, includes matter in many forms, energy in several states, radiation moving through space, and space itself expanding over time. None of these elements exists in isolation. Each influences the others, and together they determine how the universe changes. At the largest scale, the universe appears remarkably uniform. When astronomers look far away in any direction, they see similar patterns. Galaxies grouped into clusters, clusters arranged along vast filaments, and large regions where matter is sparse. This structure is not random, but it is also not fixed. It emerged gradually from small differences in density, early in cosmic history, and continues to evolve slowly. The behavior of this system is governed by a small number of well-tested physical laws. Gravity shapes how matter clumps together. Electromagnetism governs how atoms and light interact. Nuclear forces determine how stars shine and how elements form. On even larger scales, the expansion of space influences how all of these processes unfold over time. These laws do not change as the universe ages. What changes are the conditions under which they operate. One useful way to think about the universe as a system is to focus on balance. Early in its history, the universe was far from equilibrium. Temperatures were high, densities were uneven, and energy flowed rapidly from one place to another. These conditions allowed complex structures to form. As time passes, the same laws continue to operate, but the system moves closer to balance. Differences become smaller. Motion slows. Interactions become less frequent. Importantly, this progression does not require intent or direction. The universe does not aim toward an ending. It simply follows from how energy and matter behave when given enough time. The same patterns can be seen in smaller systems. A gas spreads evenly through a container. A battery eventually runs down as chemical differences are used up. These processes do not stop because something breaks. They stop because there is no longer a difference to drive them. When applied to the universe, this idea helps clarify what an end state would look like. It would not be empty space or sudden darkness. It would be a system in which matter is thinly spread, energy is evenly distributed, and large-scale changes become rare. The universe would still exist, but it would be largely uneventful. By viewing the universe this way, predictions about its future remain grounded. Scientists do not need to imagine new physics or sudden shifts. They extend what is already known, carefully and conservatively, across immense spans of time. This approach does not answer every question, but it provides a stable framework for understanding what is likely and what is not. With this system-level view in place, the next step is to look at one of the most important observations shaping our expectations, the ongoing expansion of the universe and how it sets the background for everything that follows. One of the most important facts guiding our understanding of the universe's future is that space itself is expanding. This is not a theoretical assumption, but a measured observation, confirmed through many independent lines of evidence. When astronomers observe distant galaxies, they find that light arriving from them is stretched toward longer wavelengths. This stretching indicates that the space between galaxies has increased while the light was travelling. The farther away a galaxy is, the stronger this effect appears. This expansion does not mean that galaxies are flying outward from a central point into empty space. Instead, it means that space as a whole is changing. Distances between large structures increase over time, even though those structures may remain locally bound by gravity. Within galaxies, stars continue to orbit. Within solar systems, planets continue their paths. Expansion becomes noticeable only when looking across vast cosmic distances. For predictions about the universe's end, expansion serves as the baseline behaviour. It is the background trend against which all other processes must be considered. If expansion continues, matter becomes increasingly spread out. Regions that are already far apart grow even more isolated from one another. Over time, this separation affects how energy and matter interact. Early in the universe's history, matter was dense enough that gravity could easily pull gas together to form stars and galaxies. Expansion was present even then, but it was slower relative to the strength of gravitational attraction in dense regions. As the universe grew larger, average density decreased. Gravity still operates, but its influence becomes more localized. Large-scale growth of new structures gradually slows. This observation leads to an important stabilization of the idea of an ending. Expansion alone does not destroy structures. It simply changes the conditions under which structures can form. Existing galaxies can remain intact for extremely long periods. What changes is the likelihood that new large-scale structures will emerge. Expansion shifts the universe from a state of frequent interaction to one of increasing isolation. Measurements show that expansion has not slowed over time. In fact, it has accelerated. This acceleration does not feel like motion in a familiar sense. There is no sense of speed or force that could be experienced directly. It is detected statistically through careful comparison of distances and brightness across cosmic time. This trend has significant implications, but it does not introduce sudden change. It alters the long-term direction of the system gradually. By taking expansion as a given, cosmologists can outline possible futures without assuming dramatic events. The universe does not need to end in a collapse or explosion to reach a quiet state. Continuous expansion alone is enough to reduce interactions, thin out matter, and guide the system toward conditions where little changes. As this idea settles, it becomes clear that the universe's future depends not on a single event, but on how expansion interacts with other forces over time. One of those forces, subtle but powerful in its effects, is associated with what scientists call dark energy, which shapes the expansion itself. To understand why expansion behaves the way it does, scientists introduce a component called dark energy. The name can sound misleading, as it suggests a mysterious substance filling space. In practice, dark energy is a term used to describe a consistent observation. The expansion of the universe is accelerating rather than slowing down. This acceleration has been measured through careful studies of distant objects and the large-scale structure of space. Dark energy is not observed directly. Its presence is inferred from its effects. When astronomers compare how fast galaxies appear to be moving apart now with how they moved in the past, they find that expansion has increased over time. According to earlier expectations, gravity alone should have slowed expansion gradually. Instead, the opposite trend is seen. Something is counteracting gravity on the larger scales. In many models, dark energy is treated as a property of space itself. As space expands, the influence associated with dark energy does not dilute in the same way matter does. This means that, over long periods, its relative effect becomes stronger. While gravity pulls matter together locally, dark energy influences the behaviour of space across vast distances. The result is a slow but persistent acceleration. For the future of the universe, this matters because acceleration reinforces isolation. Regions that are already far apart move beyond each other's reach more quickly. Over time, even light emitted from distant galaxies may never reach us. This does not happen suddenly. It unfolds gradually, over billions and then trillions of years, as distances increase and communication between regions fades. Despite its importance, dark energy does not introduce instability into the system. It does not tear galaxies apart or disrupt local structures. Within gravitationally bound systems, its influence is negligible. Stars continue their lives. Galaxies remain intact. Dark energy shapes the overall geometry of the universe without disturbing the details of smaller scales. This distinction helps stabilize our understanding. The universe's future is not dominated by a single overwhelming force. Instead, different forces operate at different scales. Gravity governs the local, expansion and dark energy shape the global. Neither acts abruptly. Each follows steady rules that produce slow, predictable trends when extended over time. Because dark energy is described through observation rather than mechanism, scientists remain careful in their predictions. They work with what is measured, not with assumptions about ultimate causes. As long as current measurements hold, acceleration continues, and with it the gradual thinning and quieting of the cosmos. With this in mind, it becomes important to consider how expansion and gravity interact over time. Their balance determines which structures persist, which processes fade, and how the universe transitions from an active state to a quieter one. Gravity and expansion operate together, shaping the universe in a long and subtle balance. Gravity pulls matter inward, encouraging clumping and structure. Expansion, influenced by dark energy, increases the distance between large regions of space. Neither force fully cancels the other. Instead, each dominates at different scales, and the future of the universe depends on how this balance plays out over time. On smaller scales, gravity is clearly dominant. Within galaxies, stars orbit stable centers. Gas clouds collapse to form new stars when conditions allow. Even groups of galaxies can remain bound together for extremely long periods. Expansion does not interfere with these systems because the gravitational attraction within them is far stronger than the gentle stretching of space. On the larger scales, the situation reverses. Between galaxy clusters and across the vast cosmic web, expansion becomes the dominant influence. Gravity once pulled matter together into filaments and nodes, but as space grows and density drops, gravity's reach weakens, structures stop growing, new large-scale formations become increasingly rare. This division creates a universe that is stable locally, but increasingly disconnected globally. Bound regions remain active, while the space between them grows emptier. Over time, each island of matter evolves largely on its own. There is no sudden separation. The process unfolds gradually, guided by the same physical laws at every stage. One way scientists observe this balance is by studying large-scale structure. Surveys of galaxies show how matter is distributed and how that distribution changes with distance and time. These observations reveal a universe that has already entered a phase where growth is slowing. The patterns we see today are likely close to the largest structures that will ever form. As expansion continues, gravity's role becomes more limited. It maintains existing structures, but cannot easily overcome the increasing separation between regions. This does not weaken gravity itself. It simply reflects the changing conditions of the system. The universe grows larger, and interactions become less frequent. This interplay between gravity and expansion reinforces the idea that the universe's future is defined by gradual change. There is no single moment when gravity loses or expansion wins. There is only a long transition in which the balance shifts steadily, almost imperceptibly, over immense spans of time. As this balance settles, another factor becomes important: the availability of energy to sustain activity. Even in regions where gravity holds matter together, processes depend on energy gradients. Understanding how energy changes over time helps clarify what an eventual quiet state would look like. As the universe expands and structures become more isolated, the question of energy becomes central. Not how much energy exists in total, but how usable that energy remains. In physics, this distinction matters because processes depend on differences. Heat flows from warmer regions to cooler ones. Matter moves when there are gradients in pressure or density. Light does work when it travels from a source to a place where it can be absorbed. When those differences fade, activity slows. The universe contains a vast amount of energy, and that does not disappear as time passes. What changes is its distribution. Early in cosmic history, energy was highly concentrated. Temperatures were extreme, and matter was packed closely together. These conditions allowed rapid interactions. Nuclear reactions ignited easily. Radiation shaped matter. Change was frequent and fast. As expansion continues, energy spreads out. The same amount of energy occupies a larger and larger volume of space. Temperatures fall, density decreases. Over long periods, this spreading reduces the number of strong gradients available to drive processes. The universe does not run out of energy, it runs out of contrast. This idea is often summarized through the concept of entropy. Entropy describes how evenly energy is distributed within a system. When entropy is low, energy differences are large and change is easy. When entropy is high, energy is more uniform and change becomes difficult. Entropy tends to increase over time, not because of decay or failure, but because of the way energy naturally flows. In the universe, increasing entropy means that fewer processes can take place spontaneously. Stars require concentrated fuel. Motion requires uneven distributions. As matter thins and temperatures equalize, these conditions become hard to achieve. Processes do not stop suddenly. They simply become rarer and slower. This gradual loss of usable energy shapes all long-term predictions. Even in regions where matter remains bound by gravity, activity depends on energy gradients. Stars shine because they convert concentrated nuclear energy into radiation. Planets remain warm because they receive energy from nearby stars. When those sources fade, the systems persist, but they become quieter. Importantly, this transition does not imply instability. High entropy states are stable by definition. Once energy is evenly spread, there is little incentive for further change. The universe approaches this condition asymptotically, getting closer over time without ever reaching a sharp boundary. By understanding energy this way, the idea of an ending becomes clearer. The universe does not end because something goes wrong. It reaches a state where very little happens because there is little left to drive change. With this in mind, we can now look at one of the clearest signs of this transition already underway: the gradual cooling of the cosmos itself. One of the most direct consequences of expansion and energy spreading is the cooling of the universe. This cooling is not a local fluctuation or a temporary trend. It is a steady, measurable process that has been unfolding since the earliest moments of cosmic history. As space expands, radiation travelling through it is stretched, and stretched radiation carries less energy. Over time, this leads to lower average temperatures across the universe. A clear example of this process is the cosmic background radiation, a faint glow that fills all of space. This radiation is a remnant from an earlier, much hotter phase of the universe. Today it is extremely cold, just a few degrees above absolute zero. Careful measurements show that its temperature has been decreasing slowly as the universe expands. There is no sign that this trend will reverse under current conditions. Cooling matters because temperature determines what kinds of processes can occur. High temperatures allow particles to move rapidly, collide often, and form complex structures. As temperatures fall, motion slows, interactions become less frequent. Certain reactions that once happened easily become impossible. This is not a sudden cutoff. It is a gradual narrowing of what the universe can do. As the universe cools, matter also behaves differently. Gas clouds lose thermal pressure, which can help them collapse under gravity. But only when enough material remains nearby. As expansion continues, those clouds become more diffuse, and cooling alone is no longer enough to trigger new activity. Temperature and density work together, and both are trending downward on large scales. The cooling of the cosmos does not affect all regions equally at the same time. Local environments, such as galaxies and star systems, can remain relatively warm for long periods due to internal energy sources. Stars continue to shine, planets retain heat. But these are temporary conditions set against a backdrop that is steadily becoming colder and quieter. Over immense spans of time, even these local sources fade. Stars exhaust their fuel, radiation escapes into space. Without new sources of concentrated energy, temperatures continue their slow decline. The universe approaches a state where thermal differences are minimal and large-scale motion becomes rare. This cooling does not signal a dramatic end. It is simply a continuation of a long, consistent trend. By observing it today, scientists gain insight into how the universe evolves naturally, without interruption or sudden change. As cooling progresses, its effects become especially noticeable in one key area: the slowing and eventual decline of star formation, which depends on both temperature and density. Stars are among the most active objects in the universe, and their formation marks a period of high energy and structure. For a long time, it was natural to assume that stars would continue forming indefinitely. Observations now show that this is not the case. Star formation depends on specific conditions, and those conditions are becoming harder to meet as the universe evolves. Stars form when large clouds of gas collapse under their own gravity. This collapse requires enough material in one place and the right balance between gravity and internal pressure. Early in the universe, gas was abundant and relatively close together. Collisions between galaxies and dense environments made star formation common. Over time, expansion has spread this material out, reducing the frequency of such events. As gas becomes more diffuse, it takes longer for gravity to gather enough material to form new stars. In many regions, it becomes impossible altogether. Observations of distant galaxies show that star formation peaked billions of years ago and has been declining since. This decline is steady, not abrupt, and it aligns with models based on expansion and energy loss. Even within galaxies, star formation is uneven. Some regions remain active, while others have already become quiet. Gas can be consumed by earlier generations of stars or expelled by energetic events. Once this material is gone, it does not easily return. Expansion further limits the exchange of matter between distant regions, making replenishment unlikely. This slowing of star formation has important consequences for the universe's long-term future. Stars are primary sources of light, heat, and chemical complexity. They drive planetary systems and influence their surroundings. As fewer stars form, these sources become rarer. Existing stars continue to shine, but the population slowly ages. Importantly, this process does not mark a single turning point. There is no moment when the universe stops making stars. Instead, star formation becomes less common, region by region, over vast spans of time. The universe transitions from a period of frequent stellar birth to one dominated by long-lived remnants. By focusing on this trend, cosmologists gain a clearer picture of what lies ahead. The universe does not suddenly go dark. It becomes progressively dimmer as star formation winds down. This gradual shift sets the stage for a future in which only the longest-lasting stars continue to contribute light and heat, quietly marking the passage of time. As star formation continues to slow, the universe enters a phase where existing stars matter more than new ones. The stars that remain are not all the same. Their lifetimes vary widely depending on their mass and composition. Massive stars burn through their fuel quickly, shining intensely for relatively short periods. Smaller stars consume their fuel much more slowly, producing steady light over spans of time that far exceed the current age of the universe. Because of this difference, the later stages of the universe are shaped primarily by long-lived, low-mass stars. These stars form early and persist quietly, providing light and warmth long after larger stars have ended their lives. They do not dominate the sky with brilliance. Instead, they remain stable, changing very little from 1 million years to the next. As time passes, more massive stars disappear first. They exhaust their fuel, collapse, or shed their outer layers, leaving behind compact remnants. What remains is a population increasingly weighted towards small, steady stars. The overall brightness of galaxies declines, not because stars vanish all at once, but because the most luminous ones fade away earliest. This shift alters the character of the universe. Active regions become rarer, explosive events become less common. The universe grows quieter, not in the sense of sound, but in the sense of change. Processes that once occurred frequently now happen only occasionally. The sky becomes dominated by faint, persistent sources rather than dramatic ones. Over immense spans of time, even these long-lived stars move toward exhaustion. Their fuel consumption is slow, but it is not infinite. As they age, their output gradually decreases. The light they produce becomes weaker, and the energy they provide to surrounding systems diminishes. This transition happens without a clear boundary. There is no moment when starlight suddenly ends. By focusing on the behavior of the last stars, scientists gain insight into how activity fades naturally. The universe does not require an external force to quiet it. It follows from the lifetimes of its own components. With fewer stars forming and existing ones slowly aging, attention turns to what remains after starlight becomes rare, and how the remnants of stellar evolution shape the far future. When the era of active starlight gradually gives way to a quieter universe, what remains are the remnants left behind by earlier generations of stars. These objects are not rare or exotic outliers. They are the natural outcome of stellar evolution, and over very long periods of time they become the dominant form of matter within galaxies. White dwarfs, neutron stars, and black holes persist long after stars like the Sun have completed their active phases. White dwarfs form when stars of moderate size exhaust their nuclear fuel and shed their outer layers. What remains is a dense core, no longer producing energy through fusion, but still retaining heat from its earlier life. This heat is released slowly, over billions and then trillions of years. The process is extremely gradual. A white dwarf does not switch off. It cools steadily, becoming dimmer with time as its internal energy spreads outward into space. Neutron stars are even denser remnants, formed when more massive stars collapse under gravity. They're compact and stable, held together by forces that resist further collapse. Like white dwarfs, neutron stars do not generate new energy in the way stars do. They radiate away what they have. Slowly and predictably, over long durations, they too cool and fade, becoming increasingly difficult to distinguish from their surroundings. Black holes represent another outcome, formed when gravity overwhelms all other forces during the collapse of very massive stars. Despite their reputation as destructive objects, black holes are remarkably simple in their long-term behavior. Once formed, they are stable and long-lived. They do not actively consume their surroundings unless material happens to fall into them. In a universe where matter becomes more diffuse and interactions grow rarer, such opportunities decrease rather than increase. As these remnants accumulate, galaxies change in character. Instead of being sites of ongoing creation, they become collections of long-lasting objects, each evolving slowly and independently. Motion continues, orbits remain, but the intensity of activity declines. The universe becomes dominated by persistence rather than transformation. This phase does not mark an ending in any immediate sense. It represents a shift in what kinds of processes are common. Energetic reactions give way to passive cooling. Bright sources are replaced by faint ones. Change becomes subtle, stretched across enormous spans of time. By considering these remnants, scientists can extend predictions far beyond the era of starlight. The universe does not empty out. It settles into a state where matter remains, but activity is minimal. With this foundation in place, it becomes possible to consider the longest-lasting objects of all, and how even they are subject to slow change over time. Among the remnants that persist into the far future, black holes stand out because of their extreme longevity. They are often described as final objects, places where matter and energy are permanently locked away. In reality, even black holes are part of the universe's long, gradual evolution. Their changes are slow, subtle, and governed by the same physical principles that shape everything else. A black hole forms when matter collapses so completely that gravity prevents anything nearby from escaping easily. Once formed, it can remain stable for extraordinarily long periods of time. In a universe where interactions become rare, most black holes simply persist, largely unchanged, as space around them continues to expand and cool. They do not grow rapidly. They do not dominate their surroundings. They exist quietly, shaped more by absence than by action. Over extremely long timescales, however, black holes are expected to change. According to well-established theoretical work, black holes are not entirely isolated from the rest of the universe. They slowly lose mass by emitting a very faint form of radiation. This process is not violent and not observable on human timescales. It unfolds over durations so vast that even trillions of years are only a beginning. This gradual loss does not contradict the stability of black holes, it reinforces it. The process is steady and predictable, governed by simple relationships between mass, temperature, and time. Larger black holes change more slowly than smaller ones. In fact, the most massive black holes may persist longer than any other structures in the universe, outlasting stars, planets, and even galaxies as recognizable systems. What matters here is not the technical detail, but the pattern. Even the most extreme objects do not escape gradual change. There is no permanent exception to the universe's overall tendency toward uniformity and balance. Black holes do not mark an abrupt end. They are part of a long tale of evolution, stretching far beyond the era of light. As black holes very slowly lose mass, the energy they release spreads thinly into the surrounding space. This contribution is small, but it follows the same direction as all other processes. Energy becomes more evenly distributed, and large differences continue to fade. By including black holes in this picture, the future of the universe becomes more complete. Nothing needs to happen all at once. No single object defines the ending. The universe continues its quiet progression, guided by simple rules applied over immense time. With even black holes subject to change, attention can now turn to the broader framework that describes this eventual state of balance, often referred to as heat death. The idea known as heat death is often misunderstood as dramatic or catastrophic ending. In scientific terms, it is neither. Heat death describes a condition in which the universe reaches a state of maximum entropy, meaning that energy has become as evenly distributed as possible. It is a description of balance, not destruction, and it emerges naturally from the processes already discussed. In this framework, the universe does not collapse or disappear. It continues to exist, but without strong gradients in temperature, pressure, or energy. These gradients are what allow processes to occur. When they are absent, large-scale change becomes unlikely. The universe becomes stable in a very specific sense. There is little left to drive further evolution. This state is approached gradually. It is not reached at a particular moment, and it does not occur everywhere at once. Different regions move toward equilibrium at different rates, depending on local conditions and histories. Over vast spans of time, however, the overall trend is clear. Energy differences diminish, interactions become rare, and the universe grows increasingly uniform. Heat death does not imply absolute stillness. Particles continue to exist. Space continues to expand. Small-scale motion may persist. What changes is the absence of organized activity. There are no new stars forming, no significant sources of concentrated energy, and no large-scale structures evolving in meaningful ways. This framework fits closely with current observations. Expansion continues, the universe cools, star formation declines, remnants persist and slowly fade. Each of these trends points in the same direction, without requiring new assumptions or sudden transitions. Heat death is not a prediction of something extraordinary. It is an extension of what is already happening. By framing the universe's future this way, cosmology avoids the need for dramatic conclusions. There is no final event to wait for. There is only a long approach toward equilibrium. This approach can be described mathematically and conceptually, but it does not lend itself to a single image or moment. As this idea settles, it becomes useful to acknowledge that heat death is not the only model scientists have considered. It is the most widely supported under current measurements, but it is not the only possible outcome. Understanding why other models exist and why they remain secondary helps place heat death in proper context. While heat death is the most commonly discussed future scenario, it is not the only one that has been proposed. Cosmology explores multiple models, not because scientists expect all of them to occur, but because different assumptions about the universe's properties lead to different long-term behaviours. These alternatives help clarify what current observations do and do not support. One alternative is a future collapse, sometimes described as a reversal of expansion. In this model, the universe would eventually stop expanding and begin to contract, drawing matter back together. Such a scenario depends on the total amount of matter and energy in the universe and how they influence the geometry of space. Current measurements, however, show no indication that expansion is slowing in this way. Acceleration, rather than deceleration, is what observations consistently reveal. Another possibility involves expansion continuing but changing character. Some models consider whether the influence driving acceleration could strengthen over time, leading to a gradual tearing apart of large structures. These ideas are explored mathematically, but they depend on properties of dark energy that are not supported by present data. As with collapse, they remain conditional rather than expected. What these alternatives have in common is their reliance on assumptions that go beyond what is currently measured. Cosmology is careful in this respect. Models are tested against observation, and those that require unverified behaviour are treated cautiously. They are not dismissed, but they are not prioritised. This approach reinforces the overall tone of scientific prediction. The future of the universe is not described as a fixed narrative with a known ending. It is described as a range of outcomes constrained by evidence. As measurements improve, some possibilities narrow, while others gain support. By understanding these alternative models, the role of heat death becomes clearer. It is not chosen because it is dramatic or intuitive. It is favoured because it follows directly from observed expansion, cooling, and energy distribution without requiring additional assumptions. It represents continuity rather than surprise. With this perspective in place, attention can return to a broader view of time itself, and how these future states relate to scales far beyond ordinary experience. When considering any prediction about the universe's distant future, it is important to understand why scientists avoid precise timelines. Cosmology deals with processes that unfold over spans of time far longer than those directly observed. Because of this, predictions are expressed in terms of trends and limits rather than exact dates. The universe's future is described as a direction of change, not a scheduled event. Measurements today provide strong constraints on how the universe behaves. Expansion rates, background radiation, and the distribution of matter all offer clues. From these, scientists can model how conditions are likely to evolve if the same laws continue to apply. What they cannot do is specify a moment when one phase cleanly ends and another begins. The changes involved are too gradual for that kind of precision. This uncertainty does not weaken the science, it reflects its scale. When changes occur slowly, small variations in initial conditions can shift details without altering the overall pattern. Whether star formation fades slightly sooner or later does not change the fact that it fades. Whether black holes persist for one unimaginably long duration, or an even longer one, does not alter their eventual trend. For this reason, cosmology often speaks in ranges and probabilities. Scientists describe what is consistent with current observations and what would require new physics. The future of the universe is not predicted as a story with a clear final chapter. It is mapped as a landscape of possibilities, most of which differ only in detail, not in direction. This way of working keeps predictions grounded. Rather than reaching for certainty, cosmology remains aligned with what can be tested and refined. As observations improve, timelines may shift slightly, but the large-scale picture remains stable. The universe continues to expand, cool, and move toward uniformity. With this understanding, it becomes easier to place human expectations in context. The timescales involved are not just longer than human lifespans, they are longer than the lifespan of stars and galaxies. To appreciate them, the next step is to widen perspective beyond familiar scales and consider time in a more expansive way. To place the universe's future in context, it helps to widen our sense of time. Human experience is shaped by short intervals, days, years, generations. Even historical timespans feel large only because they exceed personal memory. In cosmology, these units become very small. The processes that define the universe's long-term behavior unfold over durations so extended that ordinary counting loses relevance. Astronomers work with these scales by comparing eras rather than moments. There was a time when the universe was hot and dense. There was a long period when stars formed frequently. There will be an even longer period when star formation is rare or absent. Each era blends into the next without sharp boundaries. The transitions are gradual, defined by changing rates rather than sudden shifts. On these scales, the idea of an ending becomes less about a point in time and more about a direction. The universe moves from conditions that allow frequent change to conditions that allow very little. This movement is slow enough that no observer would witness it as an event. It would be inferred only through comparison across enormous intervals. This perspective helps stabilize expectations. The universe does not rush toward its future. It drifts. Processes wind down not because they are forced to stop, but because the conditions that sustain them slowly fade. Time stretches these changes until they appear almost static when viewed from within any short window. By considering time this way, cosmology remains descriptive rather than dramatic. The future is not framed as a destination to be reached, but as a continuation of trends already observed. Expansion, cooling, and energy redistribution extend forward smoothly, without interruption. As this broader sense of time settles, it becomes easier to see why the universe's end is rarely associated with the defining moment. Many processes conclude without ceremony. They simply become less likely, then negligible. This quiet fading is not unique to the cosmos. It reflects a general pattern in physical systems, where change often disappears before anything visibly stops. As the universe moves forward through these extended spans of time, many processes conclude without a clear signal. There is often no final action that marks their completion. Instead, rates slow until they become effectively zero. In physics, this kind of ending is common. A reaction does not need to stop entirely to become irrelevant. It only needs to become so rare that it no longer shapes the system in any meaningful way. In the universe, this pattern appears repeatedly. Star formation does not end with the last star being born everywhere at once. It becomes increasingly unlikely as material spreads out and energy differences fade. Collisions between galaxies do not suddenly cease. They simply become so infrequent that entire eras pass without one occurring. Change disappears quietly, long before anything could be called finished. This is why the idea of an end can feel misleading. Many cosmic processes have no final moment that could be identified from within the universe itself. They taper off gradually, blending into a background of near stability. The universe transitions from activity to stillness without crossing a clear boundary. This kind of change without vents challenges everyday intuition. Human experience is shaped by thresholds and conclusions. In contrast, large physical systems often move smoothly from one regime to another. The universe follows this pattern. Its future is defined by diminishing differences rather than decisive outcomes. By recognizing this, cosmology avoids searching for moments that may not exist. Instead of asking when something stops, scientists ask when it stops mattering. This shift in perspective keeps predictions aligned with how physical systems actually behave over long periods. As this idea settles, the universe appears less like a story with an ending and more like a process that gradually simplifies. With fewer active transitions remaining, attention turns to the overall character of that far future state and how it fits within the broader patterns seen throughout nature. When the universe is viewed as a whole, its long-term behaviour fits within a familiar pattern seen across many physical systems. Complexity tends to arise when conditions allow strong contrasts. Over time, those contrasts diminish, and systems move towards simpler states. This does not imply failure or decay. It reflects the natural redistribution of energy and matter. In the universe, this pattern appears at every scale. Early on, small differences in density grew into stars and galaxies. Later, those structures evolved and stabilized. Far in the future, the same structures persist but change very little. The system does not reverse direction. It continues along a path of gradual smoothing. This perspective helps place the universe's future alongside other natural processes. Rivers flatten landscapes over long periods. Heat spreads until temperatures equalize. Motion slows as energy disperses. These changes are not driven by intention or external influence. They follow from the basic rules governing energy and matter. By focusing on pattern rather than outcome, cosmology maintains a consistent description of the universe. The future is not treated as an exception to the past. It is a continuation under the same principles. Expansion continues. Energy spreads, activity becomes rare. This framing avoids assigning special meaning to any particular moment. The universe does not reach a point where it suddenly becomes something else. It gradually approaches a stable condition where large-scale change is unlikely. That condition is not an endpoint in the usual sense. It is a long-lasting state. With this understanding, the question of when the universe ends becomes less central. What matters is how it behaves, as change slows and structure persists. The final stages are not dramatic. They are quiet and extended, consistent with the patterns already observed. As this wider context settles, the exploration can return gently toward the present, connecting these distant futures with the continuity of the universe as it exists now. As the universe continues along this path of gradual simplification, its far future is best described as quiet rather than empty. Matter remains, space continues to expand, and time continues to pass. What fades is not existence itself, but activity. The universe becomes a place where change is slow and subtle, unfolding over intervals so long that they blur into stillness. In this future, regions of matter are widely separated. Interactions between them are rare. Light travels through vast stretches of space without encountering anything to illuminate. Temperatures are low and nearly uniform. Structures that once evolved rapidly now persist in stable configurations, changing only through the slowest processes allowed by physics. This state is not marked by absence. It is marked by calm continuity. The universe does not collapse into nothing, nor does it reach a moment where time loses meaning. It simply enters a phase where large-scale evolution has largely completed its course. What remains is steady, predictable, and largely unchanged from one immense span of time to the next. Importantly, this future is not separate from the present. It grows directly out of what is happening now. Expansion today sets the conditions for isolation later. Cooling now leads naturally to uniform temperatures in the distant future. The same laws that govern the universe at this moment continue to apply without interruption. By seeing the future this way, it becomes easier to release the need for a dramatic ending. The universe does not require one. Its history and its future form a continuous flow, with no sharp division between activity and rest. The transition is gradual, extended, and consistent. With this sense of continuity in place, attention can settle back into the present moment, where the universe is still active, still changing, and still following the same quiet principles that will guide it far into the future. As we return from these distant scales of time, it becomes clear that the universe does not move toward an ending in the way we often imagine endings to occur. It does not pause, conclude, or arrive. It continues gradually, following the same patterns that have guided it since its earliest moments. Change slows, not because something intervenes, but because the conditions that once sustained frequent change gently diminish. From this perspective, the future of the universe is not separate from its present. What happens now extends forward smoothly. Expansion continues, energy spreads, structures persist and slowly quiet. There is no dividing line between activity and rest, only a long transition where motion becomes less pronounced and differences become smaller. This continuity allows the idea of an ending to soften. Instead of a final moment, there is an ongoing process. The universe does not stop, it settles. Time does not break, it stretches. The same physical laws remain in place, applied patiently over durations far beyond ordinary experience. Within this steady motion, nothing needs to be resolved. The universe does not move toward absence, but toward balance. Its future is not a destination, but a state approached gradually, without urgency or interruption. Everything flows. Sleep in that motion.